Morning, afternoon, everyone. I'm Ravi. Today we'll go over this excellent paper on Amazon DynamoDB, which talks about the journey of DynamoDB from its inception through overcoming some of the challenges and how it has evolved over the period of time. Primarily, it talks about how traffic imbalances and the monitoring systems that they had built over the period of time and the the system operations that have impacted the system operations that they have done over a period of time to address the availability and performance. So there's a lot of discussed in this paper, and so what we'll do is we'll go through what the lessons were. Uh, the paper will for this discussion will have four sections. First, the overview, the architecture, the lessons, and we'll open it up for questions. So, in terms of overview, so DynamoDB has been influenced by Dynamo and the SimpleDB database, which is their first database as a service. Uh, I think the biggest learnings that they have seen in these two systems were the predictable performance that users needed, consistency, and ease of administration. So while these two databases did exist, what they realized was it wasn't really meeting the needs of users and it wasn't able to scale. So they began their journey onto DynamoDB. And if you have to give a quick contrast between Dynamo and DynamoDB, so Dynamo was their database offering, which was single tenant, which required teams to install the software, while DynamoDB from the beginning was multi-tenant. Uh, in terms of consistency, it had tunable consistency on the Dynamo side. DynamoDB has been, it supports strong consistency. The other is availability over consistency, and this one was consistency over availability. I think the biggest difference you could see is when it comes to routing and storage. Dynamo was tightly coupled, and DynamoDB, due to the nature of its multi-tenant, it has these two separated out. There are a couple of other differences, but these few stand out uh, between these two. I mean, these are the set of differences that we see that stands out between the two systems. DynamoDB is a fully managed NoSQL cloud service, and what that implies is it offers a simple API to perform your table creation, perform the reads and writes, while the underlying infrastructure takes care of provisioning, software patching, and everything to do with the system. So it's a fully managed one. So what happens is you're not really relying on provisioning the software and all, and you just rely on just their API, which is pretty robust to perform your operations. It's multi-tenant in architecture, which means within a node, they do store information of multiple customers. So right from the beginning, they ensure that they want to better utilize the clusters nodes. So they have multiple data for multiple customers on the same node, and also they pass on their savings back to the customers. So that's one thing. The other is boundless scale. There isn't really a defined limit to how large a table can grow. So uh, they go with partitions. So they partition the tables, and you can go with infinite scaling of your tables. The other is predictable performance. This has been the core idea where they favor predictable performance over any efficiencies. So that way, it makes it much more easier for customers in terms of what their reads and writes throughputs are and latencies are. It's highly available. By default, it stores data in multiple AC. They also offer global tables, which allow for higher availabilities of 5 nines across regions. The next is flexible schema. So it doesn't mandate a schema. So users are free to use their own schema. All you need is just a primary key defined, the schema for the primary key. Other than that, what goes on into each individual row is pretty flexible. So these are the few characteristics of DynamoDB in a nutshell. Next, we'll go over the architecture. And here I'm just going to do some level setting, so all of us are on the same page as we go on to the lessons that they have shared in the paper. So a table is a collection of items. An item is a collection of attributes. Each item is uniquely identified by a primary key. And a table is divided by partitions, and it's the scaling factor is always these partitions get moved across different nodes. So that's the reason they can offer this infinite scale. And each partition has 3 replicas distributed across AZs, and they use multi-paxos for leader election and consensus. So if you see an anatomy of a request as it goes through, DynamoDB is made up of a bunch of services, at least tens of services. And anytime there is a get or a put call, the first service that handles it is the request router. The request router is responsible for all the authentication and authorization. And past that, what it does is it leverages the partition metadata cache to identify which node primary stores has the data for that particular partition. And it also uses something called a global admission controller, which controls throughput, which ensures that there is no throughput, the throughput constraints that have been defined on a table are honored. And once all of these operations are done on the request router, then the request is forwarded to the respective storage node. And yeah, this is how a typical request, read and write request goes through. You see something called an auto admin, which is primarily another service which manages the control plane request in terms of provisioning new hardware. Once it determines that a particular storage node is faulty, what it does is it tries to provision alternate nodes and then move around the data. So it's a very critical resource. So these are all the services, and a typical request goes through, touches a lot of services, and then finally onto the storage nodes. So yeah, so primarily in all of this, that the auto admin service is a pretty critical resource. Next, we'll go through the lessons, which forms a core aspect of it in this particular paper. I think these were the most insightful information that one can get in this about DynamoDB, and these are very practical problems that they have seen through and how they have overcome over the period of the last decade. The first one is around admission control. So as we noticed, or as I was stating earlier, a table is divided into partitions, and partitions is what gets stored in individual nodes or the storage nodes. The initial approach was to actually allow users to define the writes and read and write throughputs, which are called the RCU and WCU, the read and write capacity units. And the initial approach was to actually do a static quota per partition, with a limit to say that per partition you could have at any point 3,000 RCUs or 1,000 WCUs. And based on the definition of a table, internally they had defined a static quota per partition and assigned these partitions to storage nodes. One of the biggest challenges, or few of the biggest challenges, has been that there were these hot partitions, which implied that uh, the underlying systems had to do throttling to mitigate the problem of utilization of a lot of resources on a specific storage node. Despite the fact that there was additional capacity at a table level, because of the static quota definition, at an individual partition, you could notice issues with throttling. So this hot partitioning and throughput dilution kind of had a big impact on performance for customers. And they also realized that there was this non-uniform access across time and key, which is usually the case. There are usually few partitions which kind of could get a lot more data, and this implied the static quota was never meeting the goals of customers for many of the times. So what they went was with bursting and adaptive capacity. With bursting, the idea was to see if you could absorb short-term temporal spikes, which means there could be few partitions which could suddenly get a huge traffic to them. And to absorb that, they supported bursting. And what they relied on is at a storage node, for all the partitions that exist on a storage node, if at all there is unused capacity, uh, and at a partition, if that throughput, if the read or write throughput RCUs were not utilized in a minute, users could have the flexibility to carry forward for the next 5 minutes. So this way, any quota that you had could be carried forward for the next 5 minutes, and this allowed for a short-term bursts in writes or reads, and they were able to absorb this. So it's primarily targeting into the unused capacity on a node also. The other was, while this addressed the short-term spikes, there was always a challenge with long-lived spikes in traffic. The next option that they had offered was adaptive capacity, which is which follows like a PID controller, where they identify partitions which are heavily skewed or accessed, and they dynamically boost the throughput on those partitions. What this allowed was, if there was a longer spike, and overall table through utilization was low, but still certain partitions within a table, if it had higher utilization, this dynamic boosting of those partitions and gave an opportunity for users to actually repurpose the throughput that was earlier, which was more at a static level, to be more uniformly distributed. But this also came with its own downside, because these were more best efforts. Though at a particular partition, they could boost it. It also had a constraint on whether the underlying node on which that partition is on, if that node itself had the capacity to handle the additional load. So these were more best efforts, and they were more reactive, which means after the fact they could react to things. So it still had its own challenges. Then they went with something called the global admission controller. So rather than having a lot of control being done at a specific node or a partition level, they moved on to a global admission controller, which is an external service which tracks consumption of reads and writes at a global level versus partition level. And now the request routers make this request to the global admission controller to determine if the request could go through or not. And that way you have more a centralized system which could handle the decision on whether a request should go through or not. So this shows the journey of how they have started off with a static definition of allocation of resources to nodes, and then moved slowly and steadily into a dynamic approach. So yeah, this is the first lesson that they talk about in the paper. Next is on durability and correctness. So definitely durability is one of the most critical aspect in this in distributed databases, or in general in everything in distributed. So uh, in terms in this one, they talk about how they have these write ahead logs, which the write ahead logs on each storage node. Each storage node is made up of, at a partition level, is made up of a B tree for the immediate reads and writes are stored in the B tree. And then there's also write ahead log, which for every write, first is written off to the write ahead log. And these write ahead logs are archived into S3 for long-term storage. This gives them a higher orders of durability guarantees. And in terms of any failure, the approach that they adopt is to actually restore from the write ahead log. They create something called a log replica, which is to immediately first restore from the write ahead log. Hi, Nicolai. Yeah, they don't go about why a B plus tree and not an LSM. They did discuss about uh, just the B plus tree aspect over here. I think it's just to do with they do this both. The logging is an additional write ahead log. They have that, uh, and the B plus tree is for quicker access. But anybody else knows that, please feel free to chime in. I don't have that answer.
As far as I know, they had started with InnoDB like a long time ago, and I don't know, that's what they had at the time. Probably LSM trees was not in fashion back then.
Could be. Okay, thanks for that. The next, it talks about the silent data errors, which are quite often in a large distributed system. So one thing which they talk about is around checksums. So they use checksums a lot on all the data that's been written to ensure there is data integrity across. And these checksums are used for all the offline validations to ensure the data that's been copied over into the offline into S3. They ensure there is continuous verification of that data by validating against checksums. Yeah, it just talks about the continuous verification, which is the scrub process, which is to ensure everything that's written off to this to offline S3 and the live replicas, they all have the same state of the data. So this is a continuous process that they run uh, to ensure the system is honoring the durability guarantees. On software bugs, they talk about using formal methods uh, to catch software bugs, subtle bugs in the replication protocol, and ensure correctness. So these are all the things that they do when it comes to durability and correctness. They go into details around primarily around the hardware failures and how they try to address it. So this was pretty insightful, targeting primarily the durability aspect. On high availability, uh, they offer two types of tables. One is the default one, which offers 4 levels, 4 nines availability, and then the global tables, which offer the 5 nines availability. And to ensure consistent reads and writes, it's always the leader that handles the request, and it's responsible for replicating writes to the replicas, and it's also is the one which is responsible for the reads. And at times when one of the replica is down, to ensure durability or to guarantee the higher durability and availability, what they do is the leader adds a log replica, which behaves something like which is like a replica, but it just doesn't have the B tree. And all it does is the leader writes to the write ahead log for this log replica. And this is to give higher durability guarantees. The other is on failure detection. Uh, this here they employ because they use this multi-pack source for replication, and on this one, on the false detection, on the failure detection of replicas becoming unavailable, they do send these heartbeats on a regular cadence. And if one of the replica is identifies that the leader is unavailable, what they also do is to send that heartbeats to the other replicas to validate and confirm. So this is like a two-way validation to minimize the false positives, because anytime there's a failure, it incurs a lot of actions downstream. So they want to prevent the false positives. So the replicas send heartbeats to the other replicas to validate. In terms of deployments, they talk about how they run the upgrade and downgrade tests to ensure there is no impact to the customers, given the multi-tenant nature and the fact that it is a cloud offering. They run a lot of these upgrade downgrade tests prior to every deployment. And they also have this nice paper which talks about the read write deployment strategy, which is to ensure for any upgrades, they first roll out the read, ensure that they can capture on both the versions, so the current version, the upgrade, the newer version, nodes can understand both the versions of API requests, you could say, and then support even the right side. So this paper talks about how they do this read write deployment and the strategy that they follow. I've attached it as a link in this. The next one, which is around predictable performance. I think this has been one of the core tenet, I would say, about DynamoDB in terms of ensuring they can offer this predictable performance to customers. Here they talk about the importance of caches and the metastability failures that they have experienced over the period. So initially, I think as we saw in the previous slides, the request router queries the partition metadata service to fetch the metadata about which node holds the data for that particular partition. So because it's rarely that the tables partitions move around, what they had was they noticed a high cache hit rate, primarily because a lot of this data was being cached, and since nothing really changes so dynamically, they were getting a 99.75 hit rate, which was great for performance, and it yielded great results. But what happened during a cold start was the system experienced this bimodal failure behavior, where in terms of a new router request router coming in, it would incur almost a 400% spike in volume to the table to DynamoDB itself to fetch the metadata information. So I think here it talks about the importance of avoiding a metastable failure, and they had incurred a high. I think there was a SEV which talked about how this led to a catastrophic during one of the peak season for them. And to overcome this failure, where this is like a typical metastable failure with caches, they developed a new fleet of service called MemDS, which is an in-memory data store, which captures this partition metadata, but it's replicated across a fleet of services, and they used a Merkle tree, which is a combination of Patricia and Merkle tree, to support these key prefix matches. And now the request routers actually, they do hold a cache of the partition metadata, which they get from MDS in-memory cache servers. For MDS, do they use consistent hashing? So it's the same copy that exists for all the MDS servers. So it's like it's just the same copy which is existing on all the servers. So I believe it's not using any consistent hash. Did that answer that question, Nicole? Okay. So yeah, this MemDS is just caching all the data for all partition. Earlier it was in the partition metadata service. Now it's all moved to the MemDS service. And there is again a cache even on the request routers. But the only thing they have ensured now is to avoid the cases where uh, these the read amplifications to servers in cases of a cache miss. What they do is, for even though they get a hit with their local cache, they still make a call to memds. So now this way, what it ensures is there is a consistent rate of requests to memds servers, and the memds servers actually get the data from the underlying partition metadata service that keeps feeding the data to it. So in a way, it's moved to something like this, which is the memds fleet has all the metadata information, and request routers keep the cache locally. They still get that same high cache hit, but they also ensure that there is a request made to the memds despite a cache hit. That way, the memds fleet always receives a constant rate of, it understands what's the peak load at any point of time, which was missing earlier, where if the data wasn't existing, it was making a call to the partition metadata service to fetch that information. So this is another lesson which is pretty critical, I felt. To one, it offers this predictable performance to ensure they can guarantee the predictable performance. The second was this metastable failure that can happen with cache. Yeah, so these are the 4 lessons that they talk about in this paper widely. And yeah, with that, I would like to open it up for questions and discussions.